All right, please stop your screen.
Yes.
And we are moving to our next presenter. It's Jerzy Chrząszcz from Warsaw, Poland, and the title of his presentation is Imperceptible Detection of Fluorescence Using TRIZ to See the Invisible. Jerzy, the screen is yours.
Thank you, Valerie. I'm trying to put my screen on everybody's screen. What do I do? Yes, this way, and now this way.
Okay.
Not yet, right. Can you see it?
Yes.
Thank you. Well, ladies and gentlemen, I would repeat what Oleg just said. Good morning, good afternoon, or good evening, whatever is appropriate for you. My name is Jerzy Chrząszcz, and I understand it's difficult to people outside Poland to spell it. Usually I've been presenting theoretical papers on TRIZ conferences so far, and today I'm going to talk about, oh, does it work? Not really. Oh yeah, now it works. About imperceptible detection of fluorescence, which is much more practical topic. We will start with briefly recalling what ultraviolet and fluorescence are. Then we will show the typical approach to fluorescence detection and also justify the need for imperceptible detection of fluorescent markers. The main parts of the presentation will explain how TRIZ tools were used to formulate and solve the problem, and how the generated solution idea was verified using simulation experiments. So let us begin. First of all, when a light beam touches a material object, it is usually partly reflected, partly absorbed, and sometimes also partly transmitted if it happens that object is transparent or translucent. Several other effects may also appear, but here we are only interested in reflection, making the object visible, and absorption, providing energy for the fluorescent light emission. Now, fluorescence. Fluorescence is a phenomenon of a very short emission of light generated by some materials when they are excited by radiation of sufficient energy. Photons absorbed by the material elevate the electrons to higher energy states, which are unstable in given temperatures, so that the electrons return to the ground levels immediately, generating photons again. And the spectrum, the color of the emitted light, depends on the chemical composition of the material. We know from physics that energy of an electromagnetic wave is proportional to its frequency. So the higher the frequency, or the shorter the waves are, the bigger energy they carry. Ultraviolet is a widely used way for inducing the fluorescence because it's powerful enough to elevate electrons in many materials, to pump up the electrons with energy to make them glowing in a fluorescent way. Yet its long wave part is still safe for humans, which is not so obvious, as we can see in this spectrum. So the ultraviolet is popular as a way of inducing fluorescence, and we will call it UV light for simplicity. Fluorescence is used in microbiology, mineralogy, also in forensic science and some other application areas. Fluorescent markers are also employed to protect banknotes, passports, and other documents against forgery by imprinting some markers that are only visible under UV light. Such inspection, such detection is usually explicit, so that once revealed, the markers can be seen by any person. And also a shield is typically used to cut off the excess of ambient light because the fluorescent is relatively weak. These are examples of commercially available devices for checking authenticity of documents or banknotes. The common characteristics are, as you can see, the built-in UV light source and a shielding against ambient light. This picture illustrates a situation that when we would like to check unobtrusively, in a secret way, in a hidden way, if a person has marks on skin or clothes indicating use of a paper gel thrower, which are fluorescent. Another scenario yielding similar requirements would be checking banknotes to identify those marked as coming from a bribe or ransom. For such cases, we want the detection to be, first of all, performed in the ambient light conditions, and then to be performed in a way which is imperceptible to the suspect and to the other people witnessing the examination. And this is our challenge. Here is a full diagram, a full roadmap of this project, and this is a simplified version covering the content described in the conference paper. It starts with function analysis and goes through cause-effect chains analysis and application of inventive principles to the substantiation stage, when the solution idea generated is verified by simulating system operation. For function analysis, the system was decomposed into UV light source and UV light called direct UV light to differentiate it from reflected UV light. Also, the other components of the system are optical element, as you can see, power source, switch, and case. In the super system, we have some material components, such as ambient light source, object, user, and bystander, and also some field objects, field components, I mean, modeling light beams involved, including fluorescent light, ambient light, and UV light. Here is a table reflecting the functions identified in the base system, the functions involved in marker detection as well as regular seeing was categorized as useful, while those adding to disclosing the detection and decreasing its effectiveness was categorized as harmful. It should be noticed that the detection and especially recognition of the markers is performed visually by the user, who is informed by the fluorescent light coming from the object, which is excited with the direct UV light. Because the object and the fluorescent light are supersystem components, the only contribution of the base system to the whole process of marker detection is, in fact, illuminating the object. So, in other words, the so-called detector is actually a UV lamp. In principle, the more energy the object receives from the energizing UV light, the more fluorescent light it could generate. Therefore, a strong UV light increases markers detectability, but it also makes the detection easily perceptible to others. On the other hand, the weak UV light would increase imperceptibility of the detection, but it would deteriorate its effectiveness. We can combine these engineering contradictions into a physical contradiction, stating that the direct UV light illuminating the object must be strong and it must be also weak for justified reasons. However, the detection of the fluorescent markers actually relies upon the fluorescent light, which is a response of the object from the object coming in after it is illuminated with this light. So we are not only interested in the incoming incident UV light, but also in the fluorescent light emitted, first of all, and also the reflected UV light, which might reflect, might reveal the detection to the bystanders. So the original contradiction was reformulated into a more generic version, which refers to optical changes. These contradicting requirements fortunately pertain to different actors, different participants of the process. So the optical changes must be visible to the user and they must not be visible to the bystander. And here we can obtain the target disadvantages, being the input to cause-effect analysis. Visibility of the optical changes to the user is insufficient, and it is excessive to the bystander. Now, this is an overview of cause-effect diagram with its user-related part and bystander-related part, each of them having branches referring to visibility of the markers and visibility of the UV beam. We consider excessive visibility of the UV beam in the user part because it may decrease the effectiveness of the detection, and also in the bystander part because it may disclose the detection, reveal it. Each of these branches is further analyzed in terms of brightness, contrast, and emission time. Because the different parts of this cause-effect model actually describe the same optical phenomena, the structures are similar, and the subgraphs mainly differ in opposite conditions. I mean, what is insufficient for the user is excessive for the bystander and vice versa. On top of this, several root causes identified are common because the optical phenomena are common to this use cases of the system. So they are repeated several times in this model. Some of these root causes refer to aspects which are unknown in advance or remain beyond control for other reasons, such as the amount of the fluorophore. We usually cannot know in advance how much would it be, or fluorophore composition. Also, some controllable aspects has been identified in the model. For instance, the amount of the UV light emitted by the source or the modulation of UV beam. Finally, key disadvantages were identified due to their impact on the target disadvantages and coming from their locations in the model and potential for changes. Key problems, in turn, were derived from these key disadvantages in such a way that each of these key problems addresses a subset of key disadvantages. And so solving one of these problems is expected to eliminate both the target disadvantages. To approach the first key problem, we might think about selective attenuation of the unwanted fluorescent light and UV light on its way to bystanders' eyes. Unfortunately, this method is not usable here because we want the detection to be strictly unnoticeable to all but the user who is aware of it. And so we cannot do anything about the object or the bystander. Nevertheless, we may select the second key problem and apply the other way around principle to invert the situation, to use the opposite optics and use a weak UV light and selectively enhance the object response, especially the fluorescent light, on its way to user's eyes. In other words, we are not allowed to virtually give every bystander sunglasses, but we may equip the user alone with a golden eye to see the invisible. And actually the golden eye was the code name of this project. A detector implementing this solution idea comprises UV light source, a color camera, processing system, image processing system, as we will be dealing with images of the object, and output device. The object is illuminated with a very weak UV light, so that neither the exciting beam nor the object response, that means the fluorescent light or reflected UV light, can be seen with the naked eye, what makes the detection perfectly imperceptible. The UV beam should also be modulated to make sure that we will recognize as the fluorescent markers only those patterns that appear when the UV light is on and disappear when it is off. This is the original function diagram for reference once again, and this is modified diagram with the additional components. Image processing system continuously acquires a stream of object images from the camera and processes it to detect, extract, and amplify the tiny color changes coming from the fluorescent response generated by object. And finally, the user is informed by the output device, for instance, a display in smart glasses. By using weak UV light instead of strong one, we eliminated all harmful functions from the system. And now the main useful function of the system is to inform the user, not to illuminate the object. So this is a real detector. Several experiments were performed to verify the effectiveness and the perceptibility of the proposed method of detection. And we will discuss some results here. What you see is the input data used for simulating system operation. These are publicly available images of documents protected with fluorescent markers as seen in the ambient light and in the UV light. The simplest experiment involved decreasing brightness of a UV light image and then applying a histogram correction to restore the image. Histogram correction is an algorithm that normalizes, in this case, increases, expands the brightness levels in the picture to make it more balanced. So for each of these steps, and these were 7 steps in turn, so the last sample was 128 times darker than the original. And for each of them, an output image was generated with histogram correction algorithm. What we see here are just 3 samples taken from the sequence. Every other step was taken, and for each of them, an average brightness is indicated below, being a number indicating average brightness. That means it evaluates to 0 if the image is completely black, and to maximal value, which is 255 when the image is completely white. As can be seen in the bottommost sample, even for the average brightness pretty close to 0, that means the image is almost entirely black, the restored image generated from this almost black something through histogram correction looks pretty much like the others, despite the histograms differ a lot. This processing scenario is a bit more complicated. We start with mixing additively a weighted UV light image with an ambient light image, which mimics image acquisition in strong ambient light with addition of different shares of weak UV light. And then we subtract the original image from the result and obtain a differential image, and we apply histogram correction to this image. As you can see in the results, the images obtained for 1, 10, and 100% of UV share added are visually pretty similar to each other, despite the UV shares differing by 2 orders of magnitude. This is the power of histogram correction. Yet another group of experiments aimed at verifying visibility of blinking or flicker resulting from illuminating an object with a modulated UV beam. To obtain a required effect, several sets of images were combined to generate animated GIF files. I hope you can see the blinking, especially in the right bottom corner. The blinking is visible as soon as it is sufficiently big, I mean, in terms of amplitude, and sufficiently quick in terms of frequency. And now I hope you can see that changes bigger than a few percent are visible. But if the changes get slower and more gradual, the flicker may be difficult to spot even for amplitudes as big as 40%. Concluding, the problem of imperceptible detection of fluorescence in ambient light condition was formulated, analyzed, and solved using TRIZ tools. The solution idea generated within this project was verified and developed into a patent application, one so far, but two other are coming, filed to Polish Patent Office. Interestingly, in addition to 4 inventive principles that were employed in the solution itself, also use a copy principle was heavily used during the substantiation phase, as the experiments used actually images instead of physical object and graphic software instead of physical system prototype. And also TRIZ approach was used to harden, to make more beneficial the patent claims. So this was all TRIZ project. And this is all of the story. Thank you for your attention.
Okay, Jerzy, thank you very much. Now I would like to turn to audience. Please, if you have any questions, type them in the chat window and make sure that everyone can see that. Maybe I start while others can type. Jerzy, that's interesting presentation. My question is, of course, you got a patent, but do you consider, or anyone considering now implementing this patent in a real device or real world, real application?
Thank you, Varel, for this question. As you probably know, the patent procedures are lengthy. I mean, it takes usually a few years before you got the decision. So the patent was filed some year ago. So I expect 2 more years to until any meaningful decision will be generated from the patent office.
Okay, thank you. Right, I'm looking in a chat window. No questions. Yeah, there is. No. Well, I assume there are no questions because the presentation is very clear.
Thank you, Valerie. That was nice.
Yes, and
thank you, nice Jim. Case. That was nice as well.
Very nice case.
Thank you. So if I'm free, I will get back to the audience mode.
Okay. I think that everybody appreciates your presentation. No questions.
Thank you.
Oh, yes, there is a question. Are there additional applications? Yeah, I mean, where else you can use it, this approach? Because definitely you found a new principle. Your solution incorporates a new principle. Maybe you can think about some other applications.
That's interesting question as well. I haven't mentioned that, but actually this motif was used in my TRIZ level 4 dissertation, and I got level 4 for expanded version of this. And as you know, the TRIZ procedure also contains some steps addressing other applications of the generated solution idea. And yes, indeed, this is a special case of a principle, perhaps not quite new, but an interesting one, of fooling human senses by changing parameters. I mean, if we can move something outside the perceptible range, it is still there, but people cannot acquire this in a direct way. It may be about light, it may be about sound, it may be about perhaps other physical parameters. But yes, I also proposed in this dissertation an application using this specific approach of changing parameters to move something outside perception windows for soundless, I mean quiet drones. To move the noise made by drones outside the range of hearing. Perhaps the dogs would be unhappy then if it would be in ultrasound range, but anyway.
Yeah, true.
So yes, there may be some probably additional application coming from this perspective of fooling human senses, but hiding a useful signal beneath the huge noise, for instance.
Right. And my last question will be here. Maybe I missed it. I'm sorry. Did you get your level 4?
Yes, I did.
Okay, congratulations.
Thank you very much. Right. And by the way, Oleg Abramov was my supervisor.
Oh, I see.
Thank you, Oleg.
And there is a question: golden ear from Mr. An.
Why not?
Why not?
Why not? If you have something to hear that no one else should hear, perhaps it's possible. By the way, there is a technology of directional loudspeakers used in marketing heavily and other places like museums. So there is only a small spot when you can hear the message, nowhere else. So perhaps this is not golden ear, but golden mouth.
Yeah.
Thank you.
Okay. Jerzy, thank you very much.
Thank you.
Thank you.